Hello again, it's Dom, and today we're going to talk about amino acids. Okay, and this leads on from what we were discussing with weak acids. And as you can remember, and hopefully you've read in your notes and it's on the PowerPoints, an amino acid has this structure. Okay, so this component there, that is our amino group. This component here is our acid. And this part here, the R group, is variable. So this will change, and that gives rise to the different types of amino acids. So what we need to know about is how amino acids can be affected by acid and alkali. So if we give an example of something, if we use this one, so again, just drawing it again. Now, several different things can happen. So if we were to acidify it, and if we acidify, we're adding hydrogen ions, and we get protonation of the amino group. Got to remember to put the little positive charge there on the nitrogen. Okay, so this is when we protonate with an acid. We can also deprotonate using an alkali, so something like sodium hydroxide. So we would write that as OH minus. And this time, instead of affecting the amino group, we're going to affect the acid group. So this time, what we've done with the alkali, it's removed this hydrogen on the OH, forming a negatively charged ion. Now, amino acids, this is the structure that I've shown for a general one, but actually, at a point known as the isoelectric point, they exist as a neutral molecule, but actually, I'm going to move it further down. They exist like this. And this is called a Zwitter ion. Okay, so it is neutral because we have one positive charge and we have one negative charge. Now I've introduced a new word there, the isoelectric point as well. Now an isoelectric point, this is the point where an amino acid has no net electrical charge. And you might think that, well, actually this is how it should be drawn, but in terms of chemistry, this is how we would draw it. Okay, so at the isoelectric point, it would be like this, Zwitter ion. And of course, depending on the amino acid, the isoelectric point is different. And basically, the isoelectric point is the pH where the Zwitter ion will form. Okay, so remember that. If I show you this little graph here, here's one I've prepared before. This is a pH titration curve, and with this the isoelectric point is around here. It doesn't necessarily mean that it's at pH 7, neutral. It varies depending on the type of amino acid and the side groups as well. So at this point here, I'm just going to choose a kind of midpoint there, and this is where we would find zwitterion. Okay. Remembering to put my charges on. Okay. Here we can see pH is dropping, so therefore we are protonating. So down here, so that's protonating. We've got the positive charge there on the nitrogen. We've got an extra hydrogen there on the amino group. And finally up here, we are deprotonating. So if we think about whatever the isoelectric point is, when we're below that, we get protonation. When we're above that, we get deprotonation. At the isoelectric point, we get zwitterion formation. Okay, so just try and remember. Now, when it comes to separating amino acids, they can be separated by a procedure called electrophoresis. Now, I think you may have come across electrophoresis with Louise in Unit 13 last year in biochemistry. And we're going to revisit that a little bit, and obviously we're going to put a chemical twist on it. But electrophoresis can separate a mixture of amino acids by the nature of their isoelectric points. And this is where it brings that in and how we can use that in basically in an analytical chemistry sense. Okay, so what I've got here, this is my obviously elaborate drawing of electrophoresis. The matrix is set at pH 6. Okay, so if we look at these different amino acids here, I've given 5 here: alanine, arginine, isoleucine, aspartic acid and glycine. And I've actually given you the isoelectric points, and it's easy to find them. You can easily Google isoelectric points for these and it'll come out with the numbers that you require. But what we've got to remember is what's going to occur. So this matrix is at pH 6. Okay, so first thing I would look at is the ones that are around 6. So we would know that alanine is 6.01. So it is going to be hanging around. I'll just write it as ALA. That's going to be hanging around this midpoint. Because if you remember the isoelectric point, that is when you get zwitterion formation. That molecule is neutral. It's got equal amounts of positive and negative charges. Isoleucine, 6.02. I would probably put that here as well. I'll write that as ISL. So that's around the midpoint. And in fact, glycine, ever so slightly under 6. It's 5.97, but it is still going to be around there. But obviously we've got 2 others that are vastly different. So we've got arginine first. That's 10.77. So 10.77, that is the point where we're going to find that we've got equal amounts. So if you remember from my previous graph, anything that is below the isoelectric point will be protonated. Anything above the isoelectric point will be deprotonated. So if I just bring the graph back in that I drew earlier, can we see that? Yep. Okay. So again, isoelectric point, we've got zwitterion formation. Above the isoelectric point, we get the deprotonation. Below the isoelectric point, we get protonation. So if we look firstly at arginine, it's 10.77. Okay, so at 10.77, that is when we're getting Zwitter ion formation. And basic maths, 6 is lower than 10.77. So because that pH is lower than the isoelectric point, that means that it will be protonated. If it's protonated, that means it has a positive charge. So therefore, it is going to be attracted towards the negative charge of the electrophoresis. So we can put our arginine then over this way. Okay. Same again, we look at aspartic acid. Aspartic acid, the isoelectric point is 2.98. So if we think about if this was 2.98, we get Zwitter ion formation. Above that, we would get deprotonation. Below that, we get protonation. So if we think the pH of this solution is 6, which is higher than 2.98, therefore, if it's above the isoelectric point, so 6 is higher than 2.98, we're going to get deprotonation. The aspartic acid is going to have a negative charge. Therefore, it's going to be attracted towards the positive charge of the electrophoresis. So I can just put that over that side. Now I'm hoping that will make a bit of sense to you. You're going to have to look over this. There are notes there for you to look at, the PowerPoints on Moodle. But also, like I said before, have a look on Chem Guide to give you guidance, further guidance on this. Okay, look over it again and again, and feel free to send me an email if you've got any problems, and I'll happily go through. I'll set another video up and we'll try and sort through that. Okay, so have a read through this, watch it, look at the information that's on Moodle, but also look on Chem Guide as well about amino acids. Remember about the whole usefulness of the isoelectric point, which is the point where you get Zwitter ion formation. Above that number, you get deprotonation. Below that number, you get protonation. Okay? Good luck looking through this, and stay safe, everyone. Thanks for listening.